Hi, today's video is about JVM architecture, Java Virtual Machine Architecture. So the reason why I chose this topic for the video is because that happens to be one of the favorite topics for interviewers in various companies in India. So if there is a core Java interview, you might be faced with a lot of questions regarding JVM architecture, class loading, and various data areas involved in JVM, etc. So let's see what JVM does. So the main function of JVM is to load and execute your application. And your application generally is a class file, .class file. So how do you create your .class file? Very basic. So you first edit your application file, which for this example, I've called it myapp.java. So edit that myapp.java file. Then you compile that myapp.java file. So you have various way of compiling a Java class. So you might run it through the javac command. And for example, in this case, we called javac myapp.java. And as a result, you would get myapp.class file. And this is the class file that you would want to execute. So you would call java myapp. So at the time when you called your class through the Java command, you have created JVM instance. Now let's see how does the JVM instance load and execute your class file. So here you can see that there is a loading component and there is an execution component. And as per the spec, this is called the class loader and this is called the execution engine. So the class loader is responsible for loading your application's .class files. So in the previous example, we saw Java myapp. So in this case, the class loader is responsible for loading my app.class file. And it also has to load the built-in class files that are part of the JVM. So built-in class files, for example, you have string.class, object.class, and all the collection classes, etc., etc. And then the loaded classes, which are basically bytecode instructions, are fed into the execution engine. And the execution engine is responsible for executing the bytecode. So in order to execute bytecode, the execution engine has to talk to the host operating system in order to execute the instructions finally against the machine instruction set. So for that, the execution engine makes use of native method calls. And finally, it gets translated into machine codes that will be responsible for carrying out the operations. So now let's go to further details. Because when you say class loading, the class's bytecode or the data will be loaded to something, loaded to a memory area. So in actual JVM architecture, there is one more component involved, which is the data areas or memory areas. So let's take a look at that diagram where we have the three component breakdown of JVM architecture. So here you have the first component, which is the class loader subsystem. Second is the runtime data areas. And third is the execution engine. These are the three main components of JVM architecture. Also, you can see the runtime data areas. You have 5 different data areas mentioned here. We'll go to that detail in a little while. So let's zoom into the class loader subsystem, how that works. So the class loader subsystem has 3 main phases: load, link, and initialize. So load is the part that is responsible of loading the bytecode into memory. So loading can load the .class bytecode from various sources. In general, when you call Java myapp, as in the previous example, myapp would be in the .class file. So the class loader would read it from the file system. The class loader may read from a .jar file, which contains a .class file. And it can even read from various other sources like a network socket. depending on the class loader implementation. But anyway, the load phase involves 3 different type of class loaders. So this is one of a question that is asked in a lot of interviews. What are the various class loaders, or the order of those class loaders? So here lies the answer. So you have Bootstrap class loader, which is responsible for loading Java's internal classes. So where does that internal class reside? The internal classes are inside the rt.jar that is distributed with your JVM implementation. Okay, so if you, next time when you are on your computer, just go to the JRE folder, and you might find the rt.jar under there. So that is the Bootstrap class loader. Now going into extension class loader, that is the second class loader that gets executed, which is responsible of loading additional application jars that are present in JRE lib.ext folder. So whatever jars that are present in JRE lib.ext folder, extension class loader will load and read all the .class files from those jars and give it out for the further processing. So last class loader is application class loader. The application class loader loads classes from values specified in your class path environment variable. And if you specify a -cp parameter to the Java command, the application class loader loads classes from that -cp parameter as well. So those are the 3 different class loaders in the load phase. So going on to the next phase, which is the link phase. So the link phase is where a lot of work is done. So it has 3 different phases. The link phase itself has 3 different phases. First is verify, second is prepare, third is resolve. So the verify phase basically looks at the bytecode that is loaded by the class loader and checks if that is compatible to the JVM class specification and things like that. So that is the verification phase. So you have to first verify the bytecode that is handed to me if it is a valid Java bytecode. So for that, it has to do a lot of checks, like the magic number checks, etc. So that is the class verification. So once it is verified, the prepare step happens. So the prepare step is the place where memory is allocated for the static variables inside a class file. So you might have, private static integer or something like that, right? So it's a class level variable. So the memory for that class level variable is allocated in the prepare phase. So the most important point that you should note at this point is that it's only memory allocation that is happening, and that is only for the class variables, not for the instance variables. So since it is just the memory allocation, what happens is those memory locations are initialized to default values. Suppose you have a variable like, public static Boolean is correct, equal to true, okay? But at prepare phase, memory will be allocated for Boolean, and it will be set to its default value, which is false as per JVM specification. Now comes the resolve phase. Okay, so the resolve phase is the place where all the symbolic references inside the current class are resolved. Suppose you have references to other classes or references to values in the constant pool. These are changed from symbolic to the actual reference. So though it's like depicted in a serial fashion, like verify, prepare, resolve, this might get executed slightly in parallel, or it might overlap in functionality to a certain extent sometimes based on the implementation. So these are defined in the Java specification so that the virtual machine implementers can classify the activities and then optimize for their performance. So those are the 3 steps involved in link phase, which is verify, prepare, and resolve. So the next phase of class loading subsystem is initialize. So this is the phase where static initializers of your class is run. Suppose you have a static block, static open parenthesis, close parenthesis. Anything under that static block is executed at this initialize phase. And wherever you have set values for static variables, those values are set into the memory location at this phase. So in the prepare phase, for example, we talked about a public Boolean is correct equal to true, right? So when its memory was allocated, it was set to false initially. And now in the initialize phase, its actual value that we mentioned in the code is set to that memory area. Okay, so those are the three different phases involved in class loading. So there is a bit of details that we might be interested in this area. So for example, class not found exception, right? So class not found exception happens when the class loader fails to find the bytecode corresponding to a class we mentioned. It's as simple as that. And the there is another type of exception called class def not found. Class def not found generally happens during a resolve, where you try to, suppose I'm loading a class X, and suppose we went through this loading phase, then we went to the link phase, it went through the verify because X's bytecode looks pretty good, and X is prepared. Now, suppose X is resolving to, X is referring to another class called Y. At the resolve phase, the system tries to find out class Y because X is referring to Y. So if class Y cannot be found, an exception will be thrown called class def not found for X, which wraps class not found exception for Y. So those are some certain exceptions that are attached to the class loading. So now we talked about class loader subsystem and its phases. Now let's go to the runtime data areas, the memory of Java virtual machine. So the runtime data areas basically has 5 different areas that we defined in the previous diagram. But here, first I'm showing 2 different areas, okay? So first is the method area. The method area is the place where class data, the metadata corresponding to class is stored, okay? A lot of APIs in Java Reflection API for class, the class inquires data in the method area. So, you have the static variables, you have the bytecode, you have the class level constant pool. Everything is stored in the method area. So method area is basically, is the memory allocated to the JVM. Basically, it's the system's physical machine's physical memory. For if you're talking about JVM for a computer. So that is the method area is only class data, static variables, bytecode, etc. Just what I said. So the method area is called the permgen space. So the permgen space is the place otherwise known as the method area. And by default, 64 megabytes, 64 MB is allocated for method area or permgen. So this can be tuned. Suppose your application is a huge server application that loads a lot of classes, millions of classes. In that case, you will have to tune the permgen using XX max perm size, and you can set it to a certain MB or GB as you might need it, right? So suppose your application has the permgen is very, very low corresponding. Suppose you're trying to load 1 million classes, but you never talked about max perm size. Suppose you left it at 64 MB. So your application might run into Java lang auto memory error for permgen space. Okay. So actually, since Java 8, they have gotten rid of the method area or the permgen, which is called, now it is called the metaspace in Java 8. So what they have done is moved the permgen or method area into a separate memory in the native operating system, and that is called the metaspace. So the point is, by default, there is no limit to metaspace in Java 8. So you can it can just grow as long as it can grow based on the operating system. It can just grow and occupy full memory, or it can go to the virtual memory and things like that. So that's the difference between permgen and metaspace. And metaspace again can be tuned, can be limited. Suppose you don't want it to just grow, you can limit using a certain JVM parameter that you can check out on the Java 8 JVM Java command options. Now coming over to the next runtime data area, which is heap. Heap is it's a very popular memory area in JVM, and you would have come across a lot of things to do with heap, like auto memory error for heap, etc., etc. A lot of people might have seen in their life. So heap is the place where object data is stored. So every time you instantiate an object, suppose you call something like my app equal to new my app, that object is created in the heap. So anything to do with object is created in the heap. So all the instance variables, arrays, everything is, since arrays are objects, are created in heap. So heap is a very important memory area in Java that most of the time needs to be tuned based on your application requirements. So that is tuned using -xms for the minimum size and -xmx for the maximum size. So by default, it is 1/4 of the physical memory, the XMS. So you can tune it using your parameters and adjust it as the application needs. So let's go ahead and look at the other runtime data areas. That is 3 more. So first one is the PC register. Second one is Java stacks and native method stacks. So PC register. So PC register is basically program counter registers. So it contains program counter, which is the pointer to the next instruction to be executed per thread. So suppose you are running 5 different threads, or for example, in this case, we are running thread T1, T2, and T3. So there will be program counter created for T1, pointing to the next instruction for thread 1, T2, pointing to the next instruction for T2, T3, pointing to the next instruction for T3. All these 3 will be created in the program counter registers. So that is per thread. Now Java stacks. Java stacks contains stack frame corresponding to the current method execution per thread. Suppose we have a thread that is executing 3 methods. So the Java stack for that thread, this is T1 in this case, this is T2, and this is T3. So T1 has 3 methods executing currently. So it would have pushed, suppose this method calls this method and this method. So it would have pushed first stack frame corresponding to first method. Suppose method 1 is calling method 2, so it would push the stack frame corresponding to method 2 into the stack. Suppose this method 2 is calling method 3, so it will push the stack frame corresponding to method 3 into the stack. So, and it will be popped based on how it is returning. So this is per thread. And stack frame basically contains data related to the currently executing method. So basically things like, memory area for the parameter array, the return values, the local variables within a method, and the operand stack, this is the place where the scratch area for doing operations specified in the methods. So So that is the stack frame. So per thread, Java stacks is created. So thread 1 has this stack, for example, thread 2 has this stack, and thread 3 has this stack. And suppose one of our method is invoking a native method. So that's the point when native method stack come into picture. Okay, suppose you are trying to load a DLL and run something from the DLL from your Java application, which is possible. So at that point of time, a native method stack will be created for that native method that you are calling. Okay, so that's what this example is showing. So talking about stacks, that is a very interesting point that you should be aware of. So stack basically is per method invocation, as I said, the stack frames. So let's think about a recursive algorithm, and recursive methods, as you know, are the methods that call itself for some purpose, right? There are a lot of algorithms that are popular for recursion. For example, factorial. So the recursive method calls itself. Suppose we forgot to put the exit condition, or they call it the basic condition of the recursion, so that it can be returned, right? Suppose we forgot to mention the exit criteria for recursion. So what happens? Your method calls itself infinitely. So as a result, what will happen? Stack frame for each invocation will be pushed into this stack. So it will keep on adding stack frame over stack frame over stack frame over stack frame. And as a result, what will happen is this memory area, this data area will run out of memory. Okay? And when that happens, you will get this exception called Java lang stack overflow error. Okay? And there may be certain genuine cases. So in this case, whenever the stack overflow error happens, you have to look for some recursive type calls that are going to keep on pushing stack frames and never popping them, never returning out of calls. So you would have to look for that type of scenario to resolve that issue. And maybe there are certain genuine cases where you might have to tune your Java stacks. So in that case, what you would use is the -xss parameter as shown here. And you can pass this as an argument to the Java command to mention the size of stacks that you want to maintain. So we talked about the 5 different runtime data areas, which is method area for class data, heap for object data, PC registers per thread for program counter, Java stacks per thread for keeping the current executing methods stack frame. So as I said, these 3 are per threads. Okay, these 3 are per threads, and this thread 1 cannot see what is there in the stack frame of thread 2, and thread 2 cannot see what is there in the Java stack of either of the threads, etc. So what is the significance of this? So that means whatever happens in the method execution generally executes here, and it's kind of thread safe in that aspect. Okay, at the same time, these 2 memory area are not per thread. These are created per JVM. So per JVM, you have 1 method area and 1 heap, and objects gets created in heap. Method area contains class data. Now let's go to the final point, which is the execution engine. So once the data area is loaded with the instruction to be executed, the current instruction to be executed is ready. What happens is that the Java interpreter interprets the current instruction that is there in the bytecode and executes it. So the execution engine, in a broad sense, has the following components. That is interpreter, then there is JIT compiler, just-in-time compiler, hotspot profiler, and garbage collector. So the interpreter takes bytecode instruction, looks at it, finds out what native operation has to be done, and executes that native operation. So that is done by using native method interface, which interfaces the native method libraries that are present in the JVM. So if you look at the JRE bin folder, you'll see, if you are on Windows, you'll see a lot of .dll files. So those are the platform specific native libraries that is used by the execution engine. And if you're in the Unix system or a Linux system, you would see .so or .a type of modules in the JRE bin folder, which is the native library. So there are a lot of optimization in the execution engine. So Java is nowadays very fast. So nobody should be worried about the performance aspect of it. So for example, the JIT just-in-time compiler is what it does is, suppose we have certain set of instructions that are getting executed all the time repeatedly. Those will not be interpreted again and again. Instead, what happens is the JIT compiler will on the fly compiles this set of instructions and keeps the target machine code ready for execution. So there is no more interpretation involved here. So it's only machine code execution when it's like, there are so-called hotspots that keeps on repeating in the application. So, that's what the hotspot profiler does. It just keeps an eye on the bytecodes that are running and grabs a lot of different statistics from those bytecodes that is usable in various formats. Okay, in various ways it can be used. So that is the that is the role of hotspot profiler. For example, in this case, it helps the JIT compiler to compile frequently used instructions. And now let's talk about garbage collector, which is responsible for the scavenging process, which cleans up unused classes, objects, and memory areas. So garbage collector is a very vast topic, so I won't go into details of it, but it's part of the execution engine. So that kind of summarizes the JVM architecture. So let's quickly go back and take a look at this three-component diagram that we have to have in our mind. When you're going for an interview, you should have a snapshot of this diagram in your mind. So first is the class loader subsystem. Second is the runtime data areas. Third is the execution engine. And class loader subsystem has load, link, initialize. And load is for the class loaders. Link has three different steps. You can go into details later. And initializes runs the static initializers. And in runtime data area, you have 5 different data areas, which is basically the memory space allocated for JVM, which is method area for class data, heap for object data, Java stack per thread keeps track of currently executing method and its data, and PC registers per thread, the program counters that knows what execution, what operation to execute next, and native method stacks corresponding to native methods used by the application. And execution engine, we saw, has the interpreter, JIT just-in-time compiler, JIT compiler, hotspot profiler, which is, sometimes they call it the hotspot VM. Then you have the garbage collector, which interfaces with the native libraries through native method interfaces. That summarizes the JVM architecture. And if you know enough details regarding each of these components, you can pretty much ace that interview. Good luck. Thanks.